In a lab in Hefei, China, a machine was switched on that, according to the calculations of the scientists who built it, performed a task in a matter of minutes that the most powerful supercomputer in the United States would need longer than the current age of the universe to finish. Not longer than a human lifetime, not longer than recorded history, longer than the universe itself has existed. The machine has a name, Zuchongzu 3.0. It is a superconducting quantum processor built by a team led by physicist Pan Jianwei at the University of Science and Technology of China. In March 2025, the team published their results in the peer-reviewed journal Physical Review Letters. The benchmark they ran is called random circuit sampling, the same class of test Google used in 2019 to first claim quantum supremacy. Zuchongzu 3.0 didn't just pass the test. It ran the calculation roughly a quadrillion times faster than the U.S. Department of Energy's Frontier supercomputer, the machine sitting in Oak Ridge National Laboratory in Tennessee that, until very recently, was ranked the fastest classical supercomputer on Earth. Here is the part that should stop you. For years, senior American officials, industry executives, and quantum researchers said publicly that China was behind. Not slightly behind, years behind. In 2023, a widely cited report from a Washington-based think tank concluded that the United States held a clear and sustained lead in quantum computing hardware. In early 2024, statements from figures inside the U.S. tech industry described China's quantum program as impressive but derivative, running years behind Google and IBM. The assumption, quietly baked into export controls, into research funding priorities, into the confidence of American policymakers, was that if a country was going to switch on a machine like this first, it would be the United States. That assumption is now, quietly, in pieces. Because Zuchongzu 3.0 didn't just match Google's Willow chip, unveiled a few months earlier in December 2024, on the specific benchmark both machines were tested against, the Chinese machine ran the task roughly 1,000,000 times faster than Willow did. Same category of hardware, same category of test, different result. And the Chinese team published the full protocol, the error rates, and the verification methodology in an open, peer-reviewed journal, meaning any physicist in the world can check the math. This is not a story about who has the better press release. This is a story about a physical machine, sitting in a shielded room in Hefei, that performed a computation the United States has spent years insisting was, at best, a distant possibility for China. And it performed that computation while U.S. export controls, tightened in 2022 and again in 2023, were supposed to be strangling China's access to the very components that make advanced computing possible. None of the standard explanations quite fit. Not sanctions, not brain drain, not funding gaps. Something else happened while Washington was focused elsewhere, and it happened faster than almost anyone in the American technology establishment predicted. Which raises the question the rest of this story is built around. If this machine wasn't supposed to exist yet, not on this timeline, not from this country, not on this scale, then what exactly is Zuchongzu 3.0 actually doing? And why should a benchmark most people have never heard of matter more than the headline number suggests? Because the number is not the story. What the number represents is quadrillions of times faster, billions of years compressed into minutes. It sounds like the kind of number a marketing team invents to sell a product. It isn't. And understanding why requires understanding something that most coverage of quantum computing skips entirely. Classical computers, the machines that run every phone, every server, every artificial intelligence model on Earth today, all work the same way at their foundation. They process information in bits. Each bit is either a 0 or a 1. To solve a problem, the machine steps through possibilities, one after another, in sequence, at extraordinary speed. That sequential nature is the ceiling. It is also the wall. There is a specific category of problem where that wall becomes physical. Not difficult, not expensive, physically impossible to cross with classical hardware, no matter how large you build it. Random circuit sampling is one of those problems. When you ask a classical computer to simulate the behavior of a quantum system with enough interacting particles, the number of possibilities it has to track doubles with every particle you add. 50 particles is already straining the world's largest supercomputers. 60 particles is beyond them. 70 is a problem no machine built on classical principles will ever solve in any human timeframe. Zuchongzu 3.0 has 105 qubits. Google's Willow has 105 qubits. Both machines operate in a regime where classical simulation is not slow. It is finished. The physics itself closes the door. That is what quantum supremacy actually means. It is not a marketing phrase. It is the specific moment when a quantum machine performs a calculation that no classical machine, present or future, at any budget, on any timeline, will ever be able to reproduce. Google reached that threshold first in 2019 with a 53-qubit chip called Sycamore. Chinese teams reached it shortly after with photonic systems, but the goalposts kept moving because classical algorithms kept improving, and researchers kept finding clever shortcuts. What makes the 2024 and 2025 results different is that both Willow and Zuchongzu 3.0 crossed into a regime where those shortcuts stop working. The gap is no longer negotiable. And this is where the American assumption cracked. The U.S. quantum program, backed by billions in federal funding through the National Quantum Initiative, backed by Google, IBM, Microsoft, and a network of national labs, was supposed to be the place where these thresholds got crossed first and stayed crossed. When Willow was announced in December 2024, that story held. When Zuchongzu 3.0 was published 3 months later, with a benchmark result roughly 1 million times better on the same test, that story stopped holding. The number itself doesn't determine who wins the next decade of computing. 1 million times advantage on random circuit sampling is not the same as 1 million times advantage on drug discovery, or cryptography, or materials science. Random circuit sampling is a test, not a product. What it proves is capability, not utility. But capability is what everything else is built on. You cannot run useful quantum algorithms on hardware that hasn't crossed the supremacy threshold. And China's hardware has now crossed it, on the same architecture the United States has been treating as its home turf. That leaves one question no one in Washington has answered cleanly. How did this happen, in this country, on this timeline, while the export controls designed to prevent exactly this outcome were tightening every year? The answer starts almost 15 years ago, in a decision most of the American technology establishment never took seriously. In 2011, while Silicon Valley was pouring capital into social media, ride-sharing apps, and the early days of cloud computing, the Chinese government made a decision that almost no American publication reported at the time. Quantum information science was designated a strategic national priority in China's 12th five-year plan. Not a research area, not a promising field, a strategic priority, in the same category as nuclear energy and space launch. The funding that followed was not venture capital. It was state capital, directed, patient, and measured in decades rather than quarters. The center of that effort was placed in Hefei, a city most Americans could not locate on a map. There, at the University of Science and Technology of China, a physicist named Pan Jianwei was given something that no researcher in the West had access to on the same scale: a guaranteed multi-decade runway to build quantum systems without pressure to commercialize, without pressure to publish quarterly, without pressure to compete for grants every 18 months. Pan had trained in Austria under Anton Zeilinger, one of the founding figures of experimental quantum information. He returned to China with a mandate that was almost unheard of in Western science: build the infrastructure, take the time, do not stop. By 2016, his team had launched MISSIS, the world's first quantum communications satellite. By 2020, they had demonstrated quantum key distribution across a distance of more than 4,600 kilometers. By 2021, they had built Zuchongzu 2.1, a superconducting quantum processor that already rivaled anything publicly disclosed in the United States. And by 2025, they had put Zuchongzu 3.0 into a peer-reviewed journal with a benchmark that outperformed the American state-of-the-art on the specific test that defines the field. None of this happened in secret. All of it was published. Most of it was ignored. The uncomfortable truth is that the American technology establishment spent those years telling itself a story that felt true because it had always been true. The story was that fundamental breakthroughs in advanced computing happen in the United States first, and everyone else catches up later. That story had been accurate for the transistor, for the integrated circuit, for the microprocessor, for the internet, for the graphics processor, for the modern AI stack. It felt safe to assume it would remain accurate for quantum. Then came the export controls. Starting in October 2022 and expanding through 2023, the U.S. Department of Commerce imposed some of the most aggressive technology restrictions in modern history, cutting China off from advanced semiconductor manufacturing equipment, from the highest-end AI chips, from the software tools needed to design cutting-edge processors. The logic was that without access to the latest silicon, China's advanced computing programs would stall. And in some areas, particularly in training the largest AI models, those controls have had real effect. Quantum computing was different. Quantum processors do not depend on the same supply chains. Superconducting qubits are fabricated using older, more accessible lithography techniques. The critical components are cryogenic refrigerators, microwave control electronics, and specialized materials science expertise. China had spent a decade building all of it domestically. The sanctions that were supposed to slow Chinese computing missed the one architecture where China had been quietly investing the hardest. That leaves the United States with a question it did not expect to be asking in 2025. If the tools designed to preserve the American lead did not apply to the field where the lead was thinnest, what does America actually have left as a counter? The answer exists, but it is more fragile than the public narrative suggests. The United States is not standing still. That has to be said clearly, because the temptation after a chapter like the last one is to conclude that America has already lost. It has not. But the shape of the American lead is different from what the public conversation suggests, and the places where it is thinnest are exactly the places that matter most. Start with Google. In December 2024, Google announced the Willow chip, a 105-qubit superconducting processor that achieves something Zuchongzu 3.0 has not publicly demonstrated: below-threshold error correction. This is a technical milestone that arguably matters more than raw benchmark speed. It means that as Google adds more qubits to the system, the overall error rate goes down instead of up. That property is the precondition for building a large, useful, fault-tolerant quantum computer, the kind that can run algorithms with real-world consequences. Willow proved the principle. No Chinese team has yet published a comparable result on superconducting hardware. Then there is IBM. IBM has taken a different path, focused less on flashy benchmarks and more on relentless scaling. The company's roadmap projects processors called Kookaburra and Bluejay that push toward thousands of physical qubits, connected across multiple chips through a technology called quantum interconnects. IBM already has quantum systems installed at Cleveland Clinic, at the Riken Research Institute in Japan, and at national labs across Europe. The company is building not just a machine, but an ecosystem. Microsoft is pursuing something stranger. In early 2025, the company unveiled the Majorana 1 chip, built on a class of materials called topological superconductors. The idea is that a topological qubit is inherently more stable, more resistant to the environmental noise that destroys other quantum architectures. If the approach works at scale, Microsoft could leapfrog everyone. If it does not, years of investment evaporate. That bet is still open. And behind those three names is a network the Chinese program does not have. IonQ, Quantinuum, Rigetti, Atom Computing, PsiQuantum, Quera. American startups pursuing trapped ion, neutral atom, and photonic quantum architectures in parallel. The US is not putting all its chips on one design. It is running 7 different bets simultaneously, funded by a mixture of federal grants, defense contracts, and private capital that no other country can match. That is the strength. Here is where it cracks. The advantage is measured in months, not years. On the specific benchmark that made headlines, China surpassed the American number by a factor of roughly 1 million on hardware built domestically without access to the most advanced Western fabrication tools. American labs have deeper ecosystems, but Chinese labs have faster execution loops because the funding is stable and the mandate is uninterrupted. Every time an American startup burns through a funding round, every time a research grant expires, every time a talented physicist leaves academia for a better-paying job at a hedge fund, the American position weakens by a small increment, and the increments have been adding up. There is also the workforce question. The 2024 report from the U.S. National Science and Technology Council flagged what it called a critical shortage of trained quantum engineers in the United States, projecting a shortfall of tens of thousands of specialists by the end of the decade. China is producing quantum PhDs at roughly twice the American rate. That gap does not close in a year. The American lead is real. It is also thinner than the confidence in Washington suggests, and both countries are sprinting for the same reason. It is not bragging rights. It is what quantum unlocks next, and one specific application that is already reshaping how governments think about their own secrets. Every message sent through an encrypted channel today every bank transfer, every diplomatic cable, every classified military communication, every private conversation between two people who believed no one was listening is protected by the same fundamental idea. It is easy for a computer to multiply two very large prime numbers together. It is extraordinarily difficult for a computer to take the result and figure out which two primes produced it. That asymmetry is the mathematical foundation of nearly all modern encryption. It is the invisible lock on the door of the Internet. In 1994, a mathematician named Peter Shor proved that a sufficiently large quantum computer could break that lock. Not slowly, not partially, completely. An algorithm now called Shor's algorithm can factor those enormous numbers in a fraction of the time a classical machine would need. When Shor published the paper, quantum computers with even two functioning qubits did not exist. The threat was theoretical, distant, decades away. Most cryptographers treated it the way people treat the eventual heat death of the universe. Interesting, but not something to plan around this quarter. That distance has collapsed. In 2022, the U.S. National Institute of Standards and Technology finalized the first set of post-quantum cryptographic algorithms, new mathematical foundations designed to resist attack from quantum machines. In 2024, NIST released the official standards for what it now calls post-quantum cryptography and issued guidance instructing federal agencies to begin transitioning immediately. In 2024, the National Security Agency published a timeline requiring national security systems to migrate to quantum-resistant encryption by 2035. The word immediately and the year 2035 are not in tension. They reflect the same fear. That fear has a name inside the intelligence community. It is called harvest now, decrypt later. The logic is brutally simple. A rival intelligence service does not have to wait until a working, cryptographically relevant quantum computer exists before it starts collecting encrypted data. It can intercept and store the encrypted traffic today at massive scale, sitting on drives in a data center somewhere, patient. When the machine capable of breaking that encryption comes online, whether it is 5 years from now or 15, everything in that archive becomes readable retroactively. Diplomatic cables from 2023, corporate acquisitions from 2024, intelligence source communications from 2025, all of it, decrypted at leisure by whichever nation reaches cryptographically relevant quantum first. American officials rarely say publicly that they believe this collection is already happening. Former NSA Director Mike Rogers has said it in interviews. So has the head of the UK National Cybersecurity Centre. The assumption inside the community is that adversaries, plural, are already harvesting and have been for years. This is why a machine in Hefei stops being a scientific curiosity and becomes a national security emergency. Zuchongzu 3.0 is not yet capable of running Shor's algorithm on any encryption used in the real world. Neither is Willow. Neither is anything IBM or Microsoft has publicly demonstrated. The qubit counts are too low, the error rates too high, the coherence times too short. But the trajectory is what matters. The gap between a machine that can beat a supercomputer at random sampling and a machine that can break RSA 2048 is measured in engineering, not in physics. The physics has been settled since 1994. The country that closes that engineering gap first inherits every secret the other side ever thought was safe. And that is not even the largest prize on the table. It is only the most terrifying one. Encryption is the front that gets the headlines. It is not the front that will define the century. Behind the cryptographic race, quietly, sits a category of problem that has bottlenecked human progress for 100 years: chemistry. The behavior of atoms and electrons interacting with each other, according to the rules of quantum mechanics, is the substrate underneath every medicine, every battery, every fertilizer, every solar cell, every industrial catalyst humans have ever made. And that substrate is exactly the kind of problem classical computers cannot simulate accurately at scale. Consider what that has cost. The average new pharmaceutical drug takes roughly 12 years to develop and costs, by the most recent industry estimates, upwards of $2 billion to bring from discovery to market. Roughly 90% of drug candidates fail somewhere in clinical trials, often because the earlier simulations of how the molecule would behave inside a human body were not accurate enough. Scientists were guessing, informed guessing, but guessing. The reason they were guessing is that a molecule with even a modest number of interacting electrons is beyond what any classical supercomputer can model exactly. Approximations get used. Approximations sometimes fail. People die from diseases that might already have treatments if the underlying chemistry could be simulated with real quantum precision. A fault-tolerant quantum computer changes the physics of that problem. Not the speed, the physics. Because a quantum machine simulating a molecule is not approximating its behavior. It is running on the same principles the molecule itself runs on. That is the difference between watching a video of the ocean and standing in the water. Both give you information. Only one gives you the truth. The implications extend past medicine. Batteries are a chemistry problem. Every improvement in lithium-ion energy density over the last 30 years has come from painstaking trial-and-error experimentation with electrode materials, often taking a decade or more per breakthrough. A quantum computer capable of simulating candidate battery chemistries directly could compress that timeline dramatically. The same applies to catalysts for producing hydrogen fuel, to materials for room-temperature superconductors, to fertilizers that do not depend on the current, extraordinarily energy-intensive Haber-Bosch process, which alone consumes roughly 1 to 2% of global energy production every year. Then there is artificial intelligence itself. Every large language model, every image generator, every AI system running today was trained on data collected by humans and processed by classical computers. There is an entire layer of scientific reality underneath that data, the quantum mechanical behavior of matter, that AI has never had access to because no machine could generate it. Hartmut Neven, who runs Google Quantum AI, has publicly argued that quantum computers will eventually become indispensable for generating the training data that pushes AI beyond what human-collected data can teach it. If that is right, and there are serious scientists who believe it is, then whichever country reaches useful quantum first also gains a compounding advantage in the AI race that everyone is currently watching. Pharmaceuticals, energy, materials, artificial intelligence. These are not separate stories. They are the same story, gated by the same technology, and the country that reaches the gate first walks through into a decade of advantages that the other side will spend the following decade trying to catch up to. That is what makes the Hefei announcement more than a science headline. It is a signal about who might reach the gate, and the answer to that question, honestly examined, is not the answer the American public has been prepared for. It would be easy, at the end of a story like this, to reach for one of two familiar conclusions. The first is that China has won, that the American century is closing, that the machine in Hefei is the moment historians will point to when the balance of technological power finally tipped. The second is the opposite reflex, that this is overblown, that the US still leads in the metrics that matter, that Willow and IBM's roadmap and Microsoft's Majorana bet will hold the line. Neither conclusion is quite right. And the reason neither is right is the real point of this story. What actually happened in March 2025 is smaller and larger than either headline. Smaller because Zuchongzu 3.0 is not a machine that can break encryption tomorrow, cure cancer next year, or dismantle American technological leadership by the end of the decade. It is a research prototype that outperformed another research prototype on a specific benchmark. That is what it is, nothing more. Larger because the assumption underneath American technology policy for the last 70 years has quietly ended. That assumption was that the ceiling of what is possible in advanced computing gets set in the United States first, and other countries operate somewhere below that ceiling. It was true for the transistor, true for the microprocessor, true for the internet, the GPU, the modern AI stack. It is not obviously true anymore. And once an assumption of that size stops holding, everything built on top of it, export controls, alliance structures, workforce planning, research funding priorities, has to be re-examined. The Chinese team did not win the quantum race with the publication of Zuchongzu 3.0. Nobody has won it. What they did was prove that the race is genuinely a race, with real competitors running at real speed, and that the outcome will be decided by execution rather than by declaration. The country that funds the workforce, that maintains stable long-term research commitments, that builds the manufacturing base for cryogenic systems and specialized materials, that keeps its best physicists from drifting into other careers, that treats quantum as infrastructure rather than as a prestige project, is the country that will reach the applications that matter first. Both countries are capable of being that country. Neither is guaranteed to be. There is a specific kind of moment in the history of technology when the public conversation is still catching up to a shift that has already happened underneath it. The first working transistor in 1947 was not covered as front-page news. The launch of ARPANET in 1969 was a footnote. The first demonstration of a large language model producing coherent text in 2018 was a curiosity. In each case, the people who understood what had just happened and who acted on that understanding early ended up shaping the decade that followed. The people who waited for the mainstream to catch up ended up building on foundations laid by someone else. The machine in Hefei is that kind of moment. Not because it is the final answer to the quantum question, because it is the signal that the question is now open, that the ceiling has moved, and that the next decade of advanced computing will not be decided by which country has the strongest opening claim. It will be decided by which country still has the endurance to finish. When the next impossible machine gets switched on, it may be in California, it may be in Hefei, it may be in a lab in Munich or Tokyo or somewhere no one is watching yet. The one thing it will not be is a surprise to anyone who is paying attention now.